You're looking at something that shouldn't exist, a visitor from another star system racing through our solar system at 137,000 miles per hour. But this isn't just any interstellar object. This is 3I Atlas. And it's breaking every rule we thought we knew about comets. On July 1st, 2025, telescopes in Chile picked up a fuzzy dot moving impossibly fast. Within hours, astronomers realized they were witnessing only the third confirmed interstellar object ever detected. But as observations poured in from the Hubble Space Telescope, the James Webb Space Telescope, and observatories around the world, something became clear. This cosmic wanderer was doing everything backwards. If you're fascinated by cutting-edge space discoveries and want to support more content like this, hit that subscribe button. Also, let me know in the comments which city you're watching from. I love seeing our global astronomy community. This script is thoroughly researched using data from NASA, ESA, and peer-reviewed astronomical observations. Now, back to our cosmic mystery. Picture a typical comet. As it approaches the sun, solar radiation heats its icy surface, causing water and other frozen gases to sublimate directly from solid to vapor. This process creates the characteristic glowing coma and sweeping tail that always points away from the sun, pushed by solar radiation pressure. It's one of the most predictable phenomena in astronomy. 3I Atlas is doing the exact opposite. Instead of ejecting material away from the sun, Hubble images from July 21st, 2025 revealed something unprecedented, a dust plume shooting directly toward our star. The comet was 277 million miles from Earth when these images were captured, and what astronomers saw defied explanation. David Jewett from UCLA, leading the Hubble analysis team, discovered that all the cometary activity was happening on the sun-facing side of the nucleus, while the night side remained completely dormant. This creates what researchers call preferential sublimation. Imagine a snowball where only the sunny side melts while the shaded side stays frozen solid. But here's where it gets even stranger. When the James Webb Space Telescope turned its infrared eyes toward 3I Atlas on August 6th, 2025 ions, it found something that challenged everything we know about comet composition. Instead of the expected water vapor that dominates normal comets, Webb detected an enormous cloud of carbon dioxide stretching over 200,000 miles from the nucleus. The numbers are staggering. 3I Atlas is releasing carbon dioxide at a rate of 130 kilograms every second. That's the weight of a small car being ejected into space every single second. Meanwhile, water vapor, which should be the dominant component, is barely detectable at just 6.6 kilograms per second. This composition is completely alien to anything in our solar system. Typical comets are about 99% water ice, carbon monoxide, and carbon dioxide combined. 3I Atlas appears to be almost pure carbon dioxide with virtually no water. The implications are profound. This object has been wandering through interstellar space for potentially billions of years, longer than our entire solar system has existed. During that journey, it's been bombarded by cosmic rays, high-energy particles that strip away hydrogen atoms and fundamentally alter surface chemistry. Think of it like cosmic weathering. After billions of years of this bombardment, 3I Atlas developed a hardened, processed crust unlike anything we see on fresh comets from our Kuiper belt. This weathered surface explains why it behaves so differently from solar system comets. The backwards dust tail phenomenon has a scientific explanation rooted in thermal physics. Because only the sun-facing hemisphere is warm enough to sublimate the remaining volatiles, all the outgassing occurs from a single direction. Instead of the symmetric activity pattern we see in normal comets, 3I Atlas creates an asymmetric jet pointing directly at the sun. But the story doesn't end there. As 3I Atlas continued its approach toward perihelion, its closest point to the sun, something remarkable happened. On August 27th, 2025, the Gemini South Telescope in Chile captured deep images revealing a more traditional anti-solar tail stretching 35,000 miles behind the comet. This suggests 3I Atlas might be transitioning from its bizarre early behavior to something more familiar as solar heating intensifies. The hardened surface crust may finally be cracking, allowing smaller particles to escape and form a conventional radiation pressure-driven tail. The size of this visitor adds another layer to the mystery. Based on brightness measurements and assuming a typical asteroid-like reflectivity of 5%, 3I Atlas could be anywhere from 1,000 feet to 23 miles in diameter. If it's on the larger end of this estimate, it would be 1 million times more massive than the previous interstellar comet Nice, 2I Borisov. This size discrepancy creates a statistical puzzle. Based on current models of interstellar object populations, we should have detected thousands of smaller objects before finding something this large. The fact that we discovered 3I Atlas suggests either our models are wrong, or this object represents something fundamentally different. As October 29th, 2025 approaches, the date when 3I Atlas reaches its closest point to the Sun at 1.4 astronomical units, astronomers are watching closely. This perihelion passage will provide the ultimate test of the object's true nature. If 3I Atlas is indeed a comet, solar heating should trigger massive outgassing and potentially spectacular outbursts. If it's something else entirely, perhaps a fragment of an ancient planetary collision or an exotic type of interstellar debris, it might continue its anomalous behavior. The trajectory of 3I Atlas is equally puzzling. Most interstellar objects arrive from random directions, reflecting their chaotic journeys through the galaxy. But 3I Atlas is traveling along a path closely aligned with our solar system's ecliptic plane, the flat zone where planets orbit. This alignment is statistically unlikely for a random interstellar wanderer. Some researchers, including Harvard's Avi Loeb, have suggested more exotic explanations. The unusual trajectory, strange composition, and backward dust emission could indicate something artificial rather than natural. While this remains highly speculative, it demonstrates how thoroughly 3I Atlas has challenged our understanding. What makes this discovery particularly significant is the rarity of interstellar visitors. Before 3I Atlas, only 2 confirmed interstellar objects had been detected, Oumuamua in 2017 and Comet 2I Borisov in 2019. Each provided unique insights into conditions around other stars. Oumuamua was elongated and showed no cometary activity, suggesting it was more asteroid-like. Borisov behaved like a typical comet with water-rich composition similar to objects in our own Kuiper belt. 3I Atlas represents something entirely new, a carbon dioxide-rich object with processed surface chemistry shaped by eons in interstellar space. The scientific race to study 3I Atlas intensified after its discovery because these objects offer fleeting opportunities. No spacecraft can reach it due to its extreme velocity and distance. By early December 2025, after passing behind the Sun, 3I Atlas will begin its journey back to interstellar space, never to return. Multiple space telescopes are coordinating observations. The transiting exoplanet survey satellite detected activity as early as May 2025, when the comet was still 6 astronomical units from the Sun, too far for water ice to sublimate, supporting the carbon dioxide composition theory. NASA's SphereX mission, designed to map galaxies, made its first major discovery by studying 3I Atlas. The spacecraft detected the massive carbon dioxide cloud and confirmed the absence of significant water vapor, providing crucial data about the object's unusual chemistry. The European Space Agency's upcoming Comet Interceptor mission, scheduled to launch in 2029, might attempt to visit another interstellar object, if one is discovered with a more favorable trajectory. Until then, remote observations remain our only window into these cosmic messengers. The dust behavior of 3I Atlas is teaching us that objects shaped by interstellar environments can be radically different from anything in our solar system. The combination of cosmic ray processing, exotic ice compositions, and billion-year journeys through space creates bodies with properties we're only beginning to understand. As we continue tracking 3I Atlas through its solar encounter, each observation adds pieces to a puzzle about the nature of matter between the stars, the backward dust tail, the carbon dioxide dominance, and the processed surface chemistry paint a picture of an object forged in conditions unlike anything we've studied before. This visitor from the depths of space is more than just an astronomical curiosity. It's a time capsule from another star system, carrying chemical signatures and physical properties shaped by alien environments. Every measurement, every spectrum, every image provides clues about planetary formation processes around distant stars. The fading dust tail phenomenon reflects fundamental physics happening on an object that predates our Sun. As 3I Atlas approaches perihelion and then begins its journey back to the stars, it leaves behind new questions about the diversity of objects wandering through our galaxy. The velocity measurements tell their own story of cosmic wandering. When first detected, 3I Atlas was moving at 61 kilometers per second relative to the Sun. To put this in perspective, our fastest spacecraft, the Parker Solar Probe, reaches a maximum speed of 200 kilometers per second, only when diving close to the Sun using gravitational assists. 3I Atlas achieved nearly 1/3 of that speed through billions of years of gravitational encounters with stars, stellar remnants, and molecular clouds scattered throughout the Milky Way. Each gravitational slingshot added momentum, ratcheting up its velocity like a cosmic pinball careening between stellar obstacles. The longer 3I Atlas wandered through interstellar space, the faster it became. This extreme velocity is both evidence of its ancient journey and the reason we'll never see it again once it leaves our solar system. Temperature dynamics reveal another layer of the mystery. At its current distance of approximately 3 astronomical units from the Sun, surface temperatures on 3I Atlas reach only about negative 150 degrees Celsius on the sunlit side. This is still frigid enough to keep water ice solid, yet warm enough to sublimate carbon dioxide. The temperature differential between day and night sides creates a thermal engine that drives the asymmetric outgassing pattern. Surface modeling suggests the nucleus rotates with a period likely between 6 and 12 hours, typical for small solar system bodies. But unlike normal comets, where rotation exposes different areas to sunlight and creates variable brightness, 3I Atlas shows remarkably steady activity. This consistency supports the theory that only one hemisphere contains volatile materials capable of sublimation at current temperatures. Spectroscopic analysis from the Very Large Telescope in Chile detected something unexpected: atomic nickel vapor in the coma. Nickel is a heavy metal that requires significant energy to vaporize, suggesting either high-temperature processes occurring on or within the nucleus, or the presence of metallic particles being stripped from the surface. This metallic signature is rare in comets and adds another piece to the puzzle of 3I Atlas's exotic composition. The carbon dioxide cloud surrounding 3I Atlas extends far beyond what anyone predicted. Sphere-X measurements show CO2 molecules at distances exceeding 348,000 kilometers from the nucleus. At these distances, the gas should have been dispersed by solar wind, yet it maintains coherent structure. This suggests either continuous replenishment from the nucleus or unusual interaction mechanisms with the interplanetary magnetic field. Dust particle analysis from Hubble images reveals a size distribution unlike typical comets. Most of the ejected material consists of large grains between 10 and 100 micrometers in diameter, moving at relatively slow speeds of 2 to 22 meters per second. Normal comets produce abundance of micron dust that gets swept into spectacular tails by radiation pressure. The lack of fine dust in 3I Atlas explains why its tail appears so faint compared to its overall activity level. The ejection mechanism itself defies conventional models. In typical comets, sublimating gas creates pressure that accelerates dust particles to speeds of hundreds of meters per second. The slow velocities observed in 3I Atlas suggest either weak gas production relative to dust mass, or an unusual surface structure that inhibits efficient momentum transfer between gas and particles. Thermal modeling indicates the nucleus likely has extremely low thermal conductivity, perhaps 10 times lower than typical comet nuclei. This insulating property would create steep temperature gradients between surface and subsurface layers, potentially explaining why activity remains confined to the directly illuminated hemisphere. Heat cannot efficiently conduct to shadowed regions, keeping them below sublimation temperatures even during rotation. The interstellar journey of 3I Atlas likely began in the outer regions of another star system, possibly during a period of planetary migration or stellar encounters that destabilized its original orbit. Computer simulations suggest objects like 3I Atlas could originate from Oort cloud analogs around other stars, ejected during close passages of neighboring stellar systems or encounters with massive molecular clouds. During its billion-year voyage through interstellar space, 3I Atlas experienced conditions impossible to replicate in laboratory settings. Cosmic ray bombardment at energies exceeding 100 trillion electron volts gradually altered surface chemistry, creating complex organic molecules while simultaneously destroying simpler compounds. This radiation processing could explain the unusual ice composition and the apparent absence of primordial water. Interstellar dust accretion also played a role in shaping the object, over geological timescales. Impacts from microscopic dust grains traveling at relative velocities of 10 to 30 kilometers per second would have sandblasted the surface, creating a regolith layer potentially meters thick. This processed surface material could form an insulating barrier that affects how interior ices respond to solar heating. The timing of 3I Atlas's discovery represents extraordinary luck. Statistical models suggest objects of this size pass through the inner solar system perhaps once every few hundred years. The fact that our modern telescope networks detected it during the brief window when it was both close enough to observe and far enough from the sun to avoid interference represents a convergence of technology and cosmic timing. Multiple spacecraft are attempting coordinated observations despite the challenges. The Perseverance rover on Mars will try to image 3I Atlas during its October close approach. though the comet will appear as little more than a faint smudge in the Martian sky. The Parker Solar Probe, currently in the inner solar system DART, might detect charged particles from 3I Atlas's interaction with solar wind, providing insights into how interstellar material behaves in our heliosphere. Ground-based radar observations from Arecibo's successor facilities are attempting to determine rotation state and surface properties. Radar echoes could reveal whether the nucleus is a single consolidated body or a loosely bound rubble pile held together by weak gravity. This information would constrain formation scenarios and help explain the unusual activity patterns. The chemical inventory of 3I Atlas continues expanding as more sensitive instruments join the observational campaign. Trace amounts of hydrogen cyanide, similar to concentrations found in solar system comets, suggest some organic chemistry survived the interstellar journey. Carbon monoxide remains below detection limits, indicating either depletion during the long voyage or sequestration in the interior beyond current solar heating penetration. Isotopic ratios, if measurable, could provide the most definitive evidence of 3I Atlas's extrasolar origin. Different stellar nucleosynthesis processes create distinct isotopic signatures in carbon, oxygen, and in nitrogen. Detecting isotope ratios inconsistent with solar system values would confirm formation around another star and potentially identify the type of stellar environment where 3I Atlas originated. The gravitational perturbations caused by 3I Atlas's passage through our solar system are negligible due to its small mass, but precise astrometric measurements are tracking tiny deviations in its trajectory. These measurements could reveal the object's internal density distribution and help distinguish between solid nucleus and rubble pile scenarios. As October 29th approaches, thermal models predict surface temperatures on the sunlit hemisphere will reach approximately negative 100 degrees Celsius. This temperature threshold could trigger sublimation of more volatile species currently locked in the interior, potentially leading to outbursts or fragmentation events. Such dramatic changes would provide unprecedented insights into the internal structure and composition of interstellar material. The legacy of 3I Atlas extends beyond its immediate scientific value. This object is teaching us that interstellar space contains a diverse population of wandering bodies, with properties shaped by environments we can barely imagine. Each detection adds to our understanding of galactic evolution, stellar system formation, and the processes that govern matter in the space between stars. On August 30th, 2025, the Gemini South Telescope captured the clearest evidence yet of 3I Atlas, transitioning from its anomalous early behavior to something approaching normal cometary activity. The 56,000-kilometer anti-solar tail represents a breakthrough moment when the processed surface finally began releasing particles in the traditional pattern. But here's what this really means. We're witnessing billions of years of cosmic evolution playing out in real time. The hardened crust created by eons of cosmic ray bombardment is finally succumbing to solar heating, revealing what lies beneath. It's like watching an archaeological excavation happen in space, where each layer of sublimating material tells the story of this object's incredible journey through the galaxy.